All right, lesson 2. Today we're going to talk about Rutherford's model. Rutherford's model is basically an advancement from the atomic model when we talked about J.J. Thomson's previous model. So the Rutherford model is the discovery of the internal structure of the atom. We're talking about introducing the nucleus of the atom. So hopefully you remember from Science 10 or maybe beyond, Rutherford's experiment is what we call the gold foil scattering. The idea is that a alpha particle, a very small particle, is shot towards gold foil. It's kind of like, imagine a bullet shooting towards a piece of tissue paper. The idea is they thought that most of these particles would go straight through, but instead what they found was some deflected at small angles and then some deflected at very large angles. So once again, based off of the expected result, if we assume that we're using Thomson's model, which is this circle with small electrons kind of built within, kind of randomly spread throughout, when we shoot the alpha particle through it, these electrons are not enough to actually deflect it. You might see a slight deflection, like if an alpha particle is interacting with one of these, it might maybe draw closer towards it, but in most cases it goes straight through. But what actually happened, once again, because of the discovery of the internal structure, which is now a large positive nucleus, when these alpha particles were shot through, some of them, let's do it the other way around, because it's alpha to positive, it should then deflect at slight angles. So if another alpha particle is like this, maybe it would be deflected, once again, due to the electrostatic force between these two. If somehow the alpha particle is shot directly at the nucleus, this is a case where maybe the particle is being shot directly back. But in most cases, most of the particles would travel still straight through. So this is the why the alpha particles are scattering. Once again, because of the very small, massive positive center. And I'm going to share a little video with you guys to talk about what the nucleus is. A little bit more detail. All right, so question 1 here. What is the magnitude of the acceleration of the electron in the planetary model of the hydrogen atom if the electron and proton are only separated by a distance of 5.29 times 10 to the negative 11 meters? So in this case here, we're assuming that we're traveling in a circle. We have a proton in the center. We have an electron going around the outside. So if this is the case, we're going to say that the electrostatic force is what's causing these two to be attracted towards one another. The electrostatic force in this case, we can use the equation of KQQ over R squared. And since we're trying to solve for an acceleration, we can also make this equal to the only force, so that's a net force, which is going to be equal to ma. So in this case, if we want to solve for the acceleration of the electron, we're just going to say that is equal to the charge, Coulomb's constant, the charge of the electron, the charge of the proton, divided by the radius squared, and then divided by the mass of the electron. So if you guys pull out your calculators, we can do that real quick. So we have our calculator saying 8.99 times 10 to the 9 multiplied by 1.6 to the negative 19. And then I'm going to square that because it's 1.6 times 10 to negative 19 for the charge of the proton as well. Dividing it by the radius of 5.29 times 10 to the negative 11. And making sure I'm squaring that. And then divided by the mass of the electron, because we're talking about the acceleration of the electron and not so much of the proton. So if I do so, I end up getting an answer of 9.03 times 10 to the 22 meters per second squared. All right, so this potential energy, I'm just going to say to ignore it. If you guys want to try it, go for it. But in most cases, if they're ever asking a question like this, they will give you the energy already. Okay, and then the idea of the planetary model collapse is that if something is accelerating, we know that acceleration should produce EMR. And if you're producing EMR, therefore, we're losing energy. And it's believed that this particle should ideally collapse on itself. So as the electron is going around the proton, it will release a photon here, maybe another photon here. And because it's accelerating, we'll lose energy and therefore collapse.